Hello class, welcome once again to our uh, fourth example for our discussion on the work and energy method. Okay, so here's the fourth example. A 2,000 pound car starts from rest at point 1, as you can see in this picture. Okay, so here's the illustration. So a 2,000 pound car starts from rest at point 1. Okay, so this is point 1 here, okay, at this point, and moves without friction. Move without friction, as you can see from the orientation of this location of the car. So naturally there would be no friction in this position. Determine A, the force exerted by the truck. Okay, so exerted by the truck on the car and on the car at point 2, so at this point here. And B, the minimum safe value of the radius of curvature at point 3. So radius of curvature. Okay, so we have here, so we call it a rho 3. Radius of curvature at this point. Okay, so solve this problem. Once again, we have to apply work and energy method. So applying the principle of work and energy to determine the velocity at point 2, and apply Newton's second law to find the normal force by the truck at point 2, and apply the principle of work and energy to determine the velocity at point 3. Then apply Newton's second law to find the minimum radius of curvature at point 3, such that positive normal force is exerted by the truck. Alright, so here's the solution, class. So apply the principle of work and energy to determine the velocity of at point 2. So at this point, so we have here at rest, we have at this point, point 1, so t is equal to 0 because it is at rest, so it means that there is no velocity yet. So at t equal to 0, so T1, no, the kinetic energy at this point, point 1 is equal to 0. So at T2, so we have the velocity or the kinetic energy equal to 1 half mv2 squared. All right. So where m is equal to w over g. All right. And for the work, no work from point 1 to point 2, so this is equal to the weight from this point to this point. So we take this length. Okay, so from the definition, the work is just the product of the force, no? The force multiplied by the displacement or the distance. So F times S. So in this case, our S is equal to 40. So our work is force. We have here the weight, so multiplied by the displacement. Okay, so this is the work from point 1 to point 2. All right, then we have here from the principle of work, we have the sum, no? The sum of this kinetic energy and the work is equal to the kinetic energy at this point. Okay, so since T1 is equal to 0, because velocity at this point is equal to 0, so we have the remaining expression as this one equal to T2. The work from 1 to 2, work done from 1 to 2 equal to T2, so 0 plus. All right, so from here we can solve for, because we have W here, W on the left side, we have W on the right side, so W divided by W, meaning divide both sides by W. So what is left is 40, 1 half times V squared over G. Okay, so cross multiplying 2G. Okay, so cross multiplying 2G, so we have uh, V sub 2 squared equal to the product of this. Okay, so you just cross multiply this one, so you have this one. Okay, on the other side, we have this. What is left on the right side is V sub 2 squared. Okay, so that's why we have V sub 2 squared equal to 2 times 40 times G. Okay, so our unit here is in terms of feet, so we will use G uh, in feet, that is 32.2 feet per second squared. So we have here the gravitational acceleration as 32.2. So multiplying this, we got V sub 2, velocity at this point 2 is equal to 50.8 feet per second. Okay, so next we have apply Newton's second law to find the normal force by the truck at point 2. So at point 2, so we have here the weight of the truck of this car uh, on this surface, and there will be a normal force acting with this weight. Okay, so the acceleration is going in this direction. So applying Newton's second law to find normal force by the truck at point 2, so we have summation of the force, normal force is equal to the mass times the acceleration, meaning you have to equate these two. Okay, so summing up, we have assuming that normal force going up is positive, weight going down negative, so we have negative W plus N equal to mass times the acceleration. Okay, now this one, transposing this to other side, so remaining only N on the left side. Then we have mass, which is equal to weight. No, the mass here is equal to weight over the acceleration. Okay, and then we have an is equal to the square of the velocity v sub 2 squared divided by rho 2. So this is also given here. Okay, so rho 2 is equal to 20 feet. All right, so what is left here is, okay, so transposing w, so we have then we have g here. This becomes like this, and then we have when you substitute the value of this one, because rho is v squared, v2 v sub 2 squared divided by rho sub 2. So that is from the previous, here we have this expression here, v sub 2, which is equal to this one. So substitute this one here. Okay, so we have w multiplied by instead of v squared or v sub 2 squared, so write this equivalent. Okay, so write it here in terms of g. So we have g at the denominator, we have g at the numerator, right? Then we have feet at the denominator, we have feet at the numerator, so that is equal to 1 also. Then 40 divided by 20, that is 2. 2 times 2, 4. 4 times w, we have 4w. So 4w, when you transpose this 1w there on the other side, so we have 5w, because the whole thing here is just equal to this one. The whole thing here, if you simplify this one, this is just equal to 4w. Okay, so 4w, and then when you transpose negative W to the other side, so that becomes positive W or 1W. Then you add this by 4W, so that's why we have N is equal to 5 times W. So where W is the weight. Okay, so the weight is given in the problem. What is the weight? So the weight is given as 2,000 pounds. Okay, so 2,000 times 5, that is, we have 10,000 pounds. So that is the normal force acting on this point. Okay, so I hope you were able to understand the explanation class. Okay, so next we have up to apply the principle of work and energy to determine the velocity at point 3. Okay, so the velocity at point 3. So velocity at point 3. So to find the velocity at point 3, so we have to use this expression class. We have the kinetic energy, kinetic energy at point 1 at this point, then plus the work, work from 1 to 3 equal to T3. Okay, so we know that the velocity here at this point, V here is V sub 1 is equal to 0. Okay, so V sub 1 is equal to 0 since our T1 is dependent on this. Alright, so we got T1 here is equal to 0. That's why we have T1 equal to 0. And work from 1 to 3 is equal to 25 feet. So why is that 25 feet? Because uh, we have weight, no? Weight uh, from this point, weight multiplied by 40, okay? Then minus, this is multiplied class, weight times minus uh, weight times the height here, which is 15. Okay, so when you combined, so this is just factor out common, which is W. So W is common. So we have 40 minus 15, factor out common W, which is 40 minus 15. So that's why we got so that's why we have here W times 25. The unit is in feet. Okay, so we have here W times 25 feet equal to, so T3, so again from the kinetic energy formula, so T is equal to 1 half mv squared. So 1 half mv squared. Okay, so in this case we have T3, so this is subscript is 3, this is subscript is 3. Okay, so that's why we have here 1 half m, where our m is equal to the ratio of the weight and the gravitational force. So this is our m, v sub 3 squared. Okay, so therefore from here we can solve for v sub 3 or v squared, sorry, v sub 3 squared. Okay, so because this is 0, so we have here, and then on the left side we have the w, the weight. On the right side we have the w also, the weight. So divide both sides by w, so you have 1, no? Divide this by w is 1 times 25, so you have 25. Then you have this one also, divide by w is 1, 1 times 1 is 1. So what is left is 25 feet equal to 1 half, 1 half, or 1 times v sub 3 squared divided by 2g. Then you cross multiply. Okay, so you cross multiply this 2g, then will be able to get v sub 3 squared. Okay, so we have here this result. Then substituting, we have the gravitational acceleration as 32.2 feet per second. So we got here the velocity at this point 3.3 equal to 40.1 feet per second. Okay, so that's how to calculate the velocity at point 3. So using this concept now that we have discussed earlier in our first video on this method. Okay, now next we have to apply once again the Newton's second law of motion. So to find the minimum radius curvature at point 3. So we have to find okay, so what is this minimum radius? So we can call this as rho 3. Rho 3. Okay, this is a rho, the symbol rho, something like this. Okay, I'll rewrite that one, class. So to avoid confusion, so I have to write it as really as rho. Okay, so what is this? This is our rho. Since this is at point 3, so we'll put the subscript here as 3. Alright, so summation of the normal force along here, so equal to m times an. So again, this is here we have the weight, since n is equal to 0. So we have the weight, which is equal to, so they have the same direction as this one, equal to m times an. Alright, so since the mass is equal to the ratio of the weight and the gravitational acceleration, and we know that an is just equivalent to the square of the velocity at this point, okay, then divided by the radius of curvature. So that is our an. So remember that, class. Okay, so an is just the ratio of the velocity at that particular point, in this case at v sub 3 squared, then divided by the radius of curvature. In this case we have rho 3. Okay, so remember this formula. It's a very important formula also. So how to prove that en is equal to this one? Very simple, class. You see, we know that the acceleration, the unit of acceleration is meter per second squared, right? Meter per second squared. So on the other side, we have here velocity. Our velocity is in terms of meter per second. Okay, but this is squared, so meaning this is meter squared. Then this is also secant squared. Alright, then our rho here in terms of meter, or it can be feet. So what will happen is that meter squared divided by meter, so we have what is left here is meter. So this would be meter per secant squared. Okay, so this is just the same as here. So acceleration is in terms of meter per second squared. This ratio is also equal to meter per second squared. So that's why we have this equivalent, class. Okay, so substituting. So we have here, the result here is that we have W, okay, we have W, which is the weight, equal to mass, which is equal to weight divided by G, okay, the gravitational acceleration, multiplied by V sub 3 squared divided by rho 3, okay, divided by rho 3. And then both sides you have W, so W divided by W is 1. This one is also 1. So what happens is that the right side becomes 1. And you have on the, sorry, the left side. On the right side you have V cube squared and divided by G times P, or rho 3. Okay, so cross multiplying this, so we have therefore, I'll continue it here. Plus we have this one, cross multiply this. So we have, by the way, we have, okay, before we multiply, so I will equate this. Um, this one is already given, the v squared, v sub 3 squared. This is equal to this one. Okay, equal to this. So you can substitute it here. So meaning we have 2 times 25. Okay, we'll write the unit later. And then we have g. Okay, then our denominator is, we have g times rho 3. Okay, so it means that numerator we have g at the numerator, we have g at the denominator. So therefore the equation becomes 1 equal to what is left here. So 2 times 25, that is 50. Okay, 50, then divided by denominator is rho 3. So cross multiplying rho 3, cross multiply to the left, and therefore we have rho 3 is equal to 50. Okay, so this is equal to 50. And the unit here is in terms of feet. Alright, so this is our rho 3. Okay, so that's the solution class. Okay, so I hope you have understood the process here, how did we solve it. By the way, we have used here meter per second squared. You can also have here feet per second squared. So you will arrive at the same result. Okay. All right. So next we have to. So I think that's the solution, the total solution of this problem. And thank you very much. And I hope you were able to understand the discussion, the explanation. And hope to see you again in our future video. So bye for now.